Here are solutions to homework set number 3 for ECE 376, Embedded Systems. The first problem is, given a temperature sensor, come up with a circuit so your PIC can read temperature. Specifically, I want to know when the temperature is above 40 degrees Celsius. So this is what I want. At 40 C, it turns on. Well, to do that, I need a sensor. In this case, I've got a thermistor. As temperature goes up, resistance goes down. I want to switch at 40 Celsius, meaning plug-in temperature, 533.66 ohms. To convert that to a voltage, use a voltage divider. Kind of arbitrarily, I chose a 1K resistor. With voltage division, that means at 40 Celsius, I want to switch at 1.7398 volts. So this resistor is kind of arbitrary. It works best if these are the same and you're switching at midband, 2.5 volts, but it just chose 1K. In terms of plus minus, as temperature goes up, R goes down, voltage goes down. When it's really, really hot, Vn is 0, so I connect the plus side. So that plus is more than minus when it's really, really hot. Gives you 5 volts when hot, 0 volts when cold. Switching at 1.73 volts, switching at 40 degrees Celsius. Problem 2. Repeat, but now add hysteresis. Turn on at 45 Celsius, turn off at 40. So the procedure to do that is, that's going to be a Schmidt trigger. That's this circuit right here with positive feedback. I first want to take the resistance or temperature, convert to resistance, convert to a voltage. So come up with a voltage divider. I chose a 1K resistor, which means at 40 Celsius I'm 533 ohms, 1.73 volts. At 45 Celsius, 438 ohms, 1.52 volts. So this is where I turn off. This is where I turn on. Since the on voltage is less than the off voltage, connect to the minus input. The on voltage is 1.52 volts. That's your offset. The gain is the ratio. The gain is the change in output over change in input. Output changes by 5 volts when the input changes by 0.3-ish. Gain of 23. Make this a 23:1 ratio. And I made them 10 times, 100 times bigger, just because actually this is in parallel with R. That changes the resistance, changes the voltage, changes the data. This is 500 ohms in parallel with 200K. It does change R a little bit, but not a lot. So this is a little bit wrong, but close. And what it looks like in terms of I/O, here's the on voltage, 1.52 volts, off voltage, 1.73. And I have this kind of backwards Z pattern. That Z pattern is the positive feedback. Problem 3. Now this one's kind of tricky. I want to turn on between 40 and 45 Celsius. Well, there's kind of two ways to do this. There's many ways to do this. Two of the ways to do this is go back to problem 1. I've got a comparator. Turn on at 45 Celsius, turn on at 40 Celsius. Then in software, I want to have the output true if RB0 is true and RB1 is false. That's one way to do it. Second way, in electronics, we cover min circuits. I'm going to come up with two different functions. One is t greater than 40. The second one is t less than 45. Then take the minimum of these two voltages. Gives you between 40 and 45. So this is a min function. Flip the diodes, have a max function. Take the minimum of A and B, and what I get is this. It's true between 40 and 45. And the pull-up resistor is when both diodes are turned off. I need to specify the voltage, 1K. When either diode is turned on, this pulls it low to 0 volts, or actually 0.7 volts. Either way works, and there's other solutions as well. Fourth problem. Come up with a circuit so your PIC can drive an RGB LED. Well, in that case, I need less than 5 volts, less than 25 milliamps, so PIC can drive it directly. If I want to get 15 milliamps, here's the circuit. Pick R to set the current to 15 milliamps. If this has a 2 volt drop, 5 volts is the output, logic 1 for PIC. 3 volts at 15 milliamps, 200 ohms. 3 volts at, no, 1.8 volts at 50 milliamps is 120 ohms. 1.8 volts at 15 milliamps, 120 ohms. So this will turn on the 3 LEDs at 15 milliamps. Then in software, I can turn these on and off using pulse width modulation to get brightnesses between 0 and 100%. Kind of saying is, anything you can do in hardware, I can do in software, vice versa. Oftentimes software is easier. So that's problem 4. Problem 5 says, I want a bigger LED. How do you power a 5-watt LED at 500 milliamps? Well, a PIC can't do 500 milliamps. The on voltage is 6 to 7 volts, let's say 6.5. A PIC can't do 6.5 volts either. So what I need is a transistor switch. This will take the PIC's output. When it's 5 volts, this turns on, and the LED turns on. At 0 volts, this turns off, LED turns off. The first step is find RC. Pick RC to set the current to 500 milliamps. When this saturates, this is about 0.2 volts. That's typically what we assume for the on state. It's close to 0, but not quite. The LED from the specs is 6.5 volts when turned on. Doesn't really matter what the current is. If it's turned on, you'll have about 6.5 volts across it. The remaining voltage is across RC. Well, the remaining voltage at 500 milliamps gives you 10 ohms. To find RB, I want to specify the base current. Now the smallest it can be is IC over beta, 500 milliamps over 300. Has to be at least 1.67 milliamps, less than 25. So pick a number between 1.67 and 25. I chose 10. You could pick something else. If I choose 10 milliamps, I know this is 5 volts, this is 0.7. That arrow means diode. Voltage drop across the silicon diode is 0.7. 4.3 volts at 10 milliamps is 430 ohms. So this one's kind of arbitrary. That 10 milliamps kind of pulled out of thin air. This can vary. It'll still work. Problem 6. Write a program that outputs G3 sharp, 207.652 Hertz. To do that, I want to output a square wave. Every time, or every loop, I'm going to toggle. This is the delay. The delay in terms of clocks is 10 million divided by 2 times Hertz. It's 10 million because there's 10 million clocks per second, 2 because there's 2 edges per cycle, and Hertz is what I want. I want to toggle, or this time right here, is 24,078 clocks. Come up with a wait routine that waits 24,078. So one way that's close, here in MATLAB, just kind of showing off, I want to find out which combination of A and B is the best. So I'm going to go through every combination of A. A is an 8-bit number, can be any value between 1 and 255. B is a number between 1 and 255. For this code, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times B times A, plus the green section, 1, 2, 3, 4, plus 1 for goto, 5 times A plus 4. That's N. Calculate N for A and B. If it's closer than any previous guess, replace capital A and B with that, display it, and repeat. Go through every permutation. When you're done, that's the best I can do, and here's N. Not required on the homework, but if you want to show off, MATLAB will go through an exhaustive search, find the best value. So anyway, here's A and B. To check it, here's my code. There's resulting A and B. The main loop is right here. I'm going to count on port C, basically 0, 1, 0, 1, even, odd, wait so many clocks, repeat. If I try that, I will connect my PIC board to a speaker through an H bridge. When I connect it up, here it is. You can see that I've got the correct frequency. All right, so that one worked. That's one advantage of assembly. I can count clocks and make the code precisely right by adjusting how many instructions are in a loop. Finally, let's play lights out. With lights out, I'm going to start with some bit value, and when I hit a button, I'll turn off that light and its neighbors. The goal is to turn off all the lights. So the start is come up with a program, or a flowchart. So you're going to initialize the push buttons are input, the lights are output. When I hit a button, I'm going to wait. If port B is equal to 0, I'm waiting until I hit the button. As soon as I press it, I'll then find out which button. If it's button 7, toggle bit 7 and 6. If it's button 0, toggle 0 and 1, and likewise for all the other buttons. I'll then count how many button pushes I had, and then wait. I'm going to sit here and wait until I release the button, then come back up here. So that's my flowchart. In terms of coding, each section is a section of assembly. So this is initialize, port B is input, port C and D are output, everybody's binary. The first loop, I'm going to keep on looping as long as port B is 0. So this is actually an 8-bit test. I'm going to take port B, an 8-bit number, compare it to the number 0. That's CPFSEQ, that's the CPF command. And if it is 0, I skip, keep on looping, otherwise skip out. The next section of code is right here. If it's button 7, I go to label B7, button 6, go to label B6, and so on. Label B0, I'm going to hit it with this mask. This is one way to toggle pins. If I just want to toggle 2 pins, take this mask, exclusive OR it. Exclusive OR 0 is no change, 1 is toggle. Bit 1, I have the bit pattern 111. Change the bit pattern. I will then increment port D and then wait until I release the button. So same as we did before, move 0 to W, compare to port B. If it's equal to W, I skip out. Not equal to W, keep testing. So that's the code. Okay, so let's see how that works. Power up the board. It always powers up with all lights turned on. You see at button 0, these 2 lights turn off. Turn on, turn off, and it's counting. Button 4, those lights turn off. A little bit of bouncing here. Turn off those lights. Once all the lights are turned off, game's over. And that took me, what is that? 1-3 hex. 19 guesses. That is homework set number 3 for ECE 376.